Tonight, there is nowhere to rush, nothing to solve, nothing to carry for a while. Just let the room grow quiet around you. Let your breathing slow down a little. Let the day loosen its grip. Because tonight, we are leaving the ordinary scale of things. Not abruptly, not with noise, but gently, like drifting away from the shore of something familiar and watching the world become wider with every passing moment. Tonight, we are exploring galaxies, not just our own. Not just the bright spiral shapes we see in photographs, but ancient galaxies, hidden galaxies, giant galaxies, shattered galaxies, quiet galaxies, galaxies wrapped in dust, galaxies ruled by invisible matter, and galaxies whose light began its journey long before Earth even existed. Some of what we'll talk about may sound almost impossible. Some of it may feel strangely beautiful. And some of it may carry that soft, unsettling feeling the universe sometimes gives us. That sense that reality is much larger, much older, and much more mysterious than the human mind was built to hold all at once. But we won't rush. We'll move slowly, from one thought to the next, from one layer of the cosmos to another. And as we go deeper, the universe will become quieter, not because it grows simpler, but because its scale begins to absorb every small noise. So settle in. Let your thoughts drift outward, and let's begin with something simple. What a galaxy really is. A galaxy is often described as a collection of stars, and that's true, but it is also much more than that. A galaxy is a structure, a system, a gravitational world, a place where stars, gas, dust, radiation, magnetic fields, star clusters, planets, black holes, and invisible matter all exist together inside one vast, organized pattern. When most people imagine a galaxy, they picture a spiral, a glowing pinwheel in the dark, elegant, balanced, complete. And some galaxies really do look like that from far away. Their arms curve outward in smooth arcs. Their centers glow more brightly. Their dust lanes wind through them like dark rivers. But the truth is that galaxies come in many forms. Some are spirals. Some are rounder and older, what we call elliptical galaxies. Some are small and chaotic. Some are so faint they're difficult to detect at all. And some have shapes so strange that they seem almost like accidents frozen in time. Still, whatever shape a galaxy takes, one thing remains the same. It is held together by gravity. Gravity is the quiet architect of galaxies. It gathers matter. It binds stars into orbits. It draws in gas. It shapes motion over hundreds of millions and sometimes billions of years. Without gravity, a galaxy would not be a galaxy. It would just be scattered light. And a galaxy is huge, truly huge. Even a relatively small galaxy can hold millions or billions of stars. A large spiral like the Milky Way contains hundreds of billions. The biggest giant galaxies may contain far more. And yet, despite all that, galaxies are mostly empty space. This is one of those cosmic truths that sounds simple at first, but becomes harder to grasp the more you think about it. A galaxy can look dense in an image. It can seem full, bright, crowded, but that brightness hides enormous distances. The stars inside a galaxy are usually separated by unimaginable amounts of emptiness. If our sun were shrunk to the size of a grain of sand, the nearest star would still be miles away. So a galaxy is not a crowded city in the way our minds first picture it. It is something looser, something airy, a vast arrangement of light suspended inside darkness. For most of human history, we didn't know what galaxies were. There was the Milky Way overhead, a pale river of light visible in dark skies. And then there were a few faint smudges seen through early telescopes. At first, no one knew whether those smudges were nearby clouds or distant systems or something else entirely. It took time, better instruments, and some extraordinary observations before astronomers understood the truth. Those faint smudges were not inside our galaxy. They were galaxies of their own, island universes, vast, separate realms of stars lying far beyond the Milky Way. That realization changed everything. Suddenly, Our galaxy was not the universe. It was one galaxy among many. And then, as observations improved, the scale widened again. Many became billions. And then more than billions. The observable universe revealed itself as a place filled with galaxies in every direction. What once looked like empty darkness turned out to be crowded with structure. Not crowded on a human scale, crowded on a cosmic one. A darkness quietly full of distant systems, each with its own stars, its own history, and perhaps, somewhere inside it, worlds no one will ever know. Every galaxy is a kind of memory. Its stars preserve chemical histories, its shape preserves past encounters, its motion preserves the influence of mass. Its brightness tells us how actively it is still making new stars. And often, its most important features are hidden from sight entirely, because visible light only tells part of the story. In fact, the glowing stars we notice first are only a fraction of what a galaxy really is. And to understand that, it helps to begin with the galaxy we know best. The one we live inside. The one we rarely see clearly, precisely because it surrounds us. The Milky Way. It is strangely difficult to picture the Milky Way. Not because it is obscure, but because we are inside it. Trying to understand our galaxy from within is like trying to understand the full shape of a forest while standing among the trees. You can study the trunks around you. You can see branches overhead. You can notice light filtering through leaves. But the complete design remains hidden unless you can somehow rise above it. We cannot rise above the Milky Way, so astronomers have had to reconstruct it slowly, from maps of stars, from radio signals, from infrared surveys that see through dust, from measurements of motion, from chemistry, from the way gas and light move across the sky. What emerges is a barred spiral galaxy, a large, rotating disk of stars and gas, a central bulge crowded with older stars, a bar-shaped structure through the core, spiral arms curving outward, and beyond the bright disk, a more extended halo reaching into dark space. Our solar system lives far from the center. We orbit in one of the quieter regions of the disk, well away from the galaxy's crowded core. That is fortunate. The central regions are far denser, more active, and in many ways more chaotic. Where we live, the environment has been stable enough over long stretches of time for planets, oceans, weather, biology, and eventually consciousness to emerge. But even here, nothing is still. The Earth moves around the Sun moves through the galaxy, and the galaxy itself moves through the larger cosmos. Our solar system is orbiting the galactic center at roughly 220 kilometers per second. At that speed, it still takes around 225 million years to complete one full orbit. One galactic year. That means, since Earth formed, our planet has only gone around the Milky Way about 20 times. 20 slow circuits through the galaxy. Dinosaurs lived and vanished in a small fraction of one. Human civilization has existed for almost none of one. From the galactic point of view, everything we call history happened in almost perfect stillness. The Milky Way is large enough to hold hundreds of billions of stars. It contains star-forming regions, ancient clusters, dark nebulae, stellar nurseries, dead stars, planets, comets, black holes, and old stars, whose orbits carry them far above and below the galactic disk. And yet, the Milky Way is not a finished object. It is still changing, still evolving, still interacting with its surroundings. Around our galaxy are many smaller companions, dwarf galaxies orbiting the Milky Way like little satellites. Some are obvious, like the large and small Magellanic Clouds visible from the southern hemisphere. Others are faint enough that they were only discovered in modern surveys. These dwarf galaxies matter, not because they are large, but because they reveal how galaxies grow. The Milky Way did not form all at once in a single smooth event. Like many large galaxies, it seems to have assembled gradually, drawing in smaller systems over time. Some of those systems were fully absorbed long ago. Others are still in the process of being torn apart. One of the clearest examples is the Sagittarius dwarf galaxy. This small companion is being stretched and disrupted by the gravity of the Milky Way right now. Each time it passes through or near our galaxy, it loses stars. Those stars don't simply disappear. They become long, faint streams wrapping around the Milky Way like ribbons in the dark. That image is worth pausing on. A galaxy leaving trails of its own stars behind, as it is slowly digested by a larger one. Not in a violent instant, not in flames, but gradually, quietly, over immense spans of time. Our galaxy also has a halo of ancient stars. Some of them are older than many stars in the disk. Some likely came from smaller galaxies that merged with the Milky Way in the deep past. Astronomers can sometimes identify these immigrant stars because their chemistry is different, or because they move in unusual ways. So the Milky Way is not one pure thing. It is layered, built, a structure assembled from many histories, a galaxy made partly from other galaxies. And the deeper astronomers looked into its motion, the more they realized something else. Something even stranger. The stars and gas we can see are not enough to explain how the Milky Way holds together, or how other galaxies do. There is more mass there than visible matter can account for. A hidden structure, an invisible foundation, something that does not shine but still shapes everything. Dark matter. One of the quietest revolutions in astronomy began with a simple question. Why do galaxies spin the way they do? At first glance, the question seems straightforward. If stars orbit around the center of a galaxy, then the farther out stars should move differently than the inner ones, depending on how mass is distributed. If most of the mass were concentrated in the bright central regions, outer stars should orbit more slowly. That would be the intuitive expectation. But when astronomers measured the rotation of galaxies, they found something strange. The stars far from the center were moving too fast. Far too fast. Fast enough that, if visible matter were all that existed, they should have escaped the galaxy's grip entirely. And yet they didn't. The galaxies remained intact. The only clear explanation was that there had to be much more mass present than we could see. A hidden component. A form of matter that does not emit light, does not reflect it, does not shine in the usual way, but still exerts gravity. This became known as dark matter. The name sounds dramatic, but the idea is actually very quiet. It simply means there is matter in the universe that reveals itself, not through brightness, but through its gravitational influence. Around galaxies, dark matter seems to form halos, huge, invisible structures extending far beyond the visible stars. The Milky Way sits inside one. Andromeda sits inside one. Giant ellipticals sit inside them too. Even dwarf galaxies appear shaped by them. You can think of a visible galaxy as a lantern. The stars are the flame. The gas and dust are the glass. But the dark matter halo is the invisible hand carrying the lantern through the dark. Without that unseen support, the system would not behave the way it does. Dark matter changes the way we imagine galaxies. They are not simply glowing islands floating in empty space. They are visible structures embedded in something larger, something hidden, something that may outweigh all the visible stars, gas, dust, and planets in the galaxy many times over. And this matters not only for mature galaxies. It may have mattered from the very beginning. In the early universe, matter was not perfectly smooth. There were tiny fluctuations in density, very small differences, but over time, gravity amplified those differences. Dark matter, which does not collide and clump in quite the same way normal matter does, may have formed the first large gravitational scaffolds. Ordinary matter then fell into those scaffolds. Gas cooled. Stars formed. Galaxies took shape. In that picture, galaxies were not built from light outward. They were built from invisible structure first. The visible galaxy came later. That idea is deeply strange, and also oddly elegant. The visible universe resting on invisible architecture. Dark matter also explains something else, why galaxies can survive in the forms they do. Without extra mass in their halos, fast-moving outer stars would drift away. The graceful spiral disks we admire would become far less stable. Much of what makes a galaxy recognizable seems to depend on something we have not yet directly seen. That is one of the great humbling lessons of cosmology. The universe is not required to make its foundations obvious. What matters most is not always what shines brightest. In some cases, the hidden nature of dark matter becomes even more haunting. There may be galaxies with very few stars at all, systems rich in gas or dark matter, but poor in starlight. There are also ultra-diffuse galaxies, so faint and spread out that they are barely visible against the sky. And some structures reveal themselves mainly through their gravitational pull on nearby matter or the way they bend light from objects behind them. It is possible for a galaxy to be almost ghost-like. Still real, still massive, still present, but scarcely lit. That idea leads naturally to one of the most fascinating truths about galaxies. They do not all look the same, not even close. Once the hidden halo is there, the visible galaxy can take almost any form. Some are orderly, some are ragged, some are luminous, some are nearly invisible. Some seem as though they belong in a dream, more than in a catalog. So let's drift into those next. The odd ones. The giants. The faint ones. The galaxies that seem to resist expectation. If you browse enough images of galaxies, a quiet realization begins to settle in. The universe is creative. Not in the human sense of intention, but in the sense that a few basic forces, given enough time, can produce extraordinary variety. Spiral galaxies are perhaps the most iconic. They have disks, central bulges, and arms winding outward in elegant curves. These arms are not fixed solid structures. They may be more like patterns, regions where stars and gas bunch up temporarily as they orbit the galactic center. The shape remains, but the material inside that shape changes over time, like a traffic pattern moving through cars rather than a painted line fixed on the ground. The Milky Way is a spiral. So is Andromeda. There is something almost reassuring about them. They look orderly, balanced, as though the cosmos occasionally prefers grace. Elliptical galaxies feel different. They are rounder or more oval. They usually contain older, redder stars. They often have less gas and less active star formation. Their stars do not move in one shared, well-organized plane the way stars in a disk do. Instead, they move in many directions, a looser, more random arrangement created in part by past mergers. Ellipticals can be small or enormous. The biggest ones sit at the centers of galaxy clusters, like ancient rulers, surrounded by lesser systems. They are quiet giants, built over time through repeated collisions and accumulations. Their calm appearance hides turbulent histories. Then there are irregular galaxies. These resist neat classification. They can look messy, uneven, stretched, clumpy, or broken. Some are small galaxies that never settled into a strong spiral or elliptical form. Others were once more orderly, but were distorted by close encounters or collisions. They often contain rich gas clouds and bright young stars. From a distance, some irregulars look like torn clouds of light. Dwarf galaxies are their own world of variety. These are much smaller systems containing far fewer stars than giants like the Milky Way. Some are ancient and dim. Some are rich in gas. Some orbit larger galaxies and gradually lose material to them. Dwarfs may be among the building blocks from which larger galaxies grew, small, old pieces of a grander cosmic assembly. There are also ultra-diffuse galaxies. These are especially haunting. They may be as wide as a large galaxy, but with far fewer stars. Instead of a bright disk or bulge, they appear as pale, ghostly smudges. They are easy to miss. It is possible that many more exist than we have yet identified, hidden by their own faintness. Some galaxies look almost impossible. Ring galaxies, for example, form bright loops of stars surrounding dimmer centers. They often seem to be the aftermath of an intrusion, a smaller galaxy passing through a larger one and sending a density wave outward like a ripple in water. That ripple compresses gas and can trigger star formation in a circular pattern. The result is a galaxy shaped like a luminous ring. Then there are polar ring galaxies, where one ring or disk orbits nearly at right angles to the main body. They have an unsettling beauty, one system layered onto another, two axes of motion inside one gravitational life. These structures tell us that a galaxy's past may include the capture of outside material that never fully aligned with what was already there. And some galaxies contain counter-rotating regions, gas moving one way, stars moving the other, or a central component spinning differently from the rest. These systems preserve the memory of mergers. A galaxy may have absorbed another with its own momentum, and the new material kept that original direction rather than blending into the old one. In all these cases, shape becomes biography. A galaxy's form is not random decoration. It is evidence. It is history made visible. A ring may mark a collision. A tidal tail may mark a close pass. A warped disk may mark an encounter. A faint halo may preserve swallowed companions. A smooth, giant elliptical may mark countless mergers layered together over billions of years. And sometimes galaxies don't just change shape. They change brightness. They flare with star birth. They fall quiet. They hide behind dust. They radiate in wavelengths our eyes cannot see. They even disappear from view, only to reveal themselves by gravity. So the next layer of the story is not just about what galaxies look like. It is about what they are doing, what is happening inside them, how they live, feed, shine, and sometimes almost vanish. There is a simple reason astronomy keeps surprising us. The universe does not present itself all at once. Much of it is hidden. Not because it wants to be mysterious, but because light can be blocked, stretched, absorbed, or emitted in forms our eyes never evolved to detect. Some galaxies are hidden behind dust. Dust may sound insignificant. Something soft. Something delicate. But in galaxies, dust can change everything. It absorbs visible light and blocks our view of stars and structures behind it. In some galaxies, star formation is so active and the dust so thick that optical light alone gives a deeply incomplete picture. Yet dust does not simply swallow light and end the story. It absorbs short wavelengths and re-emits energy as infrared radiation. That means a galaxy that seems dim or obscure in visible light can glow beautifully in infrared. It was not absent, only veiled. This is why infrared telescopes transformed our understanding of galaxies. They let us look through the curtains. They revealed star-forming regions buried in dust. They uncovered galaxies in the early universe that ordinary optical surveys could barely see. They showed us that some of the most active galactic systems were not bright in the way we expected. They were bright in a different language of light. Radio astronomy reveals another hidden layer. Hydrogen, the most abundant element in the universe, emits a faint signal at a specific radio wavelength known as the 21-centimeter line. By tuning into that signal, astronomers can map gas in galaxies, including galaxies that are faint, dusty, or difficult to detect in visible light. In radio, a galaxy's structure changes. The glowing stars fade in importance. Gas becomes central. Invisible halos become easier to infer. Jets from active black holes appear as giant, elegant structures extending far beyond the visible galaxy. Some galaxies that seem quiet in ordinary images reveal astonishing power in the radio sky. There are also galaxies that appear to have very few stars at all. These are sometimes described as dark galaxies or candidate dark galaxies, not because they contain no matter, but because they contain so little visible starlight relative to their mass or gas content. They may be failed galaxies that never formed many stars, or gas-rich remnants of interactions, or systems caught in unusual stages of galactic life. Whatever their origin, they remind us of something important. A galaxy does not need to be bright to be real. It only needs mass, structure, and time. Ultra-diffuse galaxies carry a similar lesson. These systems can be huge in size, yet barely visible. Their stars spread so thinly that they appear like breath on glass. Astronomers have only found many of them in recent decades because detecting something so faint is technically difficult. They are like cosmic whispers, large enough to matter, soft enough to overlook. Some galaxies are not hidden by dust or faintness, but by distance. Their light has traveled so long and space has expanded so much during its journey that visible light is shifted into infrared by the time it reaches us. So again, without the right instruments, the galaxy would seem absent. Not because it isn't there, because it speaks at a wavelength we cannot hear unaided. And then there are galaxies we discover almost by accident, not through their own light, but through their gravitational effects. They tug on nearby structures. They disturb streams of gas. They bend light from more distant objects behind them. Even when they stay visually elusive, gravity betrays them. That is one of the most beautiful things about astronomy. When the universe hides one clue, it often leaves another. A dusty galaxy glows in infrared. A gas-rich one speaks in radio. A hot environment reveals itself in X-rays. An invisible mass leaves traces in motion. A foreground galaxy bends the image of one far behind it. Reality leaks through, even when light alone is not enough. And hidden inside many large galaxies, behind all this dust and gas and star formation, something else may be waiting. Something small compared with the galaxy's full width, yet powerful enough to dominate its center. A supermassive black hole. Sometimes quiet, sometimes bright enough to outshine the galaxy itself. At the center of almost every large galaxy, there seems to be a black hole. Not a black hole formed from a single dead star. Something far bigger. Millions or billions of times the mass of the sun. A supermassive black hole. That phrase has become familiar enough that its strangeness can fade. But if you pause and let it sink in, it is astonishing. Inside the center of a galaxy, among billions of stars, there may sit a region so dense and so gravitationally extreme that beyond a certain point, nothing escapes. Not even light. Our own galaxy has one. Sagittarius A star. For much of human history, of course, we had no idea it was there. The center of the Milky Way is hidden behind dust, and only through careful measurements of stellar motion were astronomers able to infer the presence of an immense compact mass. Stars near the center whip around as though orbiting something heavy and small. The only explanation that fits is a supermassive black hole. Andromeda has one too, larger than ours. Many giant galaxies host still larger ones. But black holes are not always obvious because they are not always active. A black hole by itself is dark. It becomes dramatic only when matter falls toward it. Gas and dust spiraling inward form an accretion disk. That disk heats up through friction and gravity until it shines intensely. In this state, the galactic center becomes an active galactic nucleus. Push the feeding rate high enough, and the result can be a quasar. A quasar is one of the brightest things in the universe. And that is such a remarkable sentence, because the source of that brightness is centered on something whose defining feature is darkness. The black hole itself does not glow. The material around it does. Matter falling toward the unseen center becomes hotter and brighter than entire galaxies of stars. Some quasars shine with the power of trillions of suns. We can see them across enormous distances, which means we see them as they were in the distant past, often when the universe was much younger. In that earlier era, quasars were more common. Young galaxies had more gas available. Their black holes had plenty to feed on. The universe was a busier, brighter place. There is something almost philosophical about quasars. A reminder that darkness can shape brightness, that absence can control radiance, that the deepest wells of gravity can turn surrounding matter into beacons visible across billions of light years. Some active galactic nuclei also launch jets. Great focused streams of particles and energy shot outward from near the black hole, not from inside it, but from the turbulent region around it. Magnetic fields twist and channel the flow. The jets can extend for astonishing distances, sometimes longer than the visible galaxy itself. In radio images, they look like luminous threads or lances stretching through space. And these black holes do more than shine. They influence the fate of the entire galaxy. When an active galactic nucleus pours out energy, it can heat nearby gas or drive it outward. Gas that is too hot or pushed too far away cannot easily collapse to form new stars. So a black hole, tiny compared with the full size of the galaxy, can regulate the galaxy's star formation. The heart can alter the future of the body. Sometimes black holes even flicker. Astronomers have seen active galaxies brighten and fade on surprisingly short timescales. These changing-look quasars remind us that galactic centers are dynamic. Matter flows in unevenly. Accretion changes. What looks stable on human intuition can shift even within years. In merging galaxies, the picture grows stranger still. When two galaxies begin to combine, their black holes do not necessarily merge immediately. For a long time, they may orbit each other as a binary pair deep inside the chaotic remnant. Two supermassive black holes, two dark hearts, moving closer over millions of years. Eventually, they may spiral together and merge, sending gravitational waves outward into space-time itself. It is difficult to think of anything more quietly magnificent. Two invisible giants drawn together by the memory of their galaxies. A merger whose final signal ripples through the fabric of reality. And all of this begins in the center, a place we often cannot see directly. A place hidden by dust, crowded with stars, packed with history. A dark center that may remain calm for ages. Then feed. Then flare. Then sleep again. But black holes are only one way galaxies change. There is another force just as important, and in some ways gentler to imagine, not the falling inward of matter, but the gathering together of galaxies themselves. Because galaxies do not live fixed, separate lives forever. They meet, they interact. And when they do, they reshape each other. A galactic collision is nothing like the word collision usually suggests. There is no sudden crash in the ordinary sense. No sharp impact. No immediate destruction. Galaxies are mostly empty space. Their stars are so far apart that when two galaxies pass through each other, direct star-on-star collisions are unlikely. Most stars simply keep going, each following the curved guidance of gravity. And yet galactic encounters are still transformative. Because gravity does not need physical contact to do its work. It stretches, it pulls, it twists orbits, it tears long streams from disks, it reshapes structure on enormous scales. Gas clouds do collide, though, and that matters. Gas can compress, shock, collapse, form new stars. So a galactic merger often triggers bursts of star formation. Regions that were once calmer become bright with newborn stars, ultraviolet light, hot dust, and the restless energy of sudden creation. This is what makes some merging galaxies look so beautiful and strange. They develop tidal tails, long arcs of stars and gas pulled outward like silk in slow motion. They form bridges between approaching systems. Their spiral arms distort, their cores brighten. Everything becomes elongated, curved, unsettled. And all of it happens slowly. A merger can take hundreds of millions or billions of years to unfold. Galaxies approach, pass through each other, swing apart, fall back, pass again. Over time, their motions lose energy. Eventually, they settle into a new form. Sometimes the result is an elliptical galaxy. The ordered disks are gone. The old graceful spiral shape has been scrambled. Stars now move on more randomized paths. Gas may be used up, heated, or expelled. New star formation declines. The remnant becomes rounder, calmer, older. A quiet giant, made from a violent memory. Sometimes the encounter creates tidal dwarf galaxies. These are smaller systems formed from material pulled out during the merger. They are made not from pristine, untouched gas, but from recycled matter. Borrowed stars. Borrowed gas. Borrowed history. That idea is lovely in its own way. A galaxy torn apart, and from the torn edges, something new begins. Our own Milky Way carries evidence of past mergers. It has absorbed smaller galaxies before. The halo preserves stars with unusual orbits and chemistries. Stellar streams mark where old companions were stretched apart. Some globular clusters may even have been acquired this way. The Milky Way is not a closed object. It is a survivor and an accretion engine, growing partly by drawing others in. And it is not done, because our galaxy has a future encounter waiting, one of the most famous in astronomy. A slow dance already underway. Andromeda is moving toward us. Right now, it hangs more than 2 million light-years away, a faint blur visible even to the naked eye in dark skies, but its motion reveals that it is approaching. Over the next several billion years, the Milky Way and Andromeda will draw together until their great disks begin to overlap. This future merger won't be sudden. It will be an era. Imagine the night sky changing over millions of years, Andromeda growing larger, its structure becoming clearer. Then the stars of two giant galaxies passing through one another, dust lanes tangling, gas clouds colliding, new waves of star formation igniting, the sky no longer resembling anything humans have ever known. And through all of it, most stars will miss each other entirely. The drama is not in direct impact. It is in gravity, the grand rearranger. Eventually, the two galaxies will settle into one larger remnant. Astronomers sometimes casually call it Milkomeda, though the final form will probably resemble a large elliptical-like galaxy more than a spiral. The solar system, if it still exists as a system by then, may survive, but its orbit within the remnant could be very different. Our cosmic address would change, even if our sun did not immediately perish from the merger itself. And beyond the stars, deep inside the remnant, the black holes from both galaxies may eventually spiral together. Two galactic hearts becoming one. This is what galaxies do. They do not remain untouched. They encounter, they distort, they combine, they pass matter onward into new forms. Nothing about them is static, except from the viewpoint of short-lived creatures like us. Given enough time, a galaxy is less like a fixed building and more like weather. Flowing, gathering, stretching, settling, changing shape again. And when galaxies collide, one of the most visible outcomes is often a period of intense creation, a bright, temporary fever of new stars, a starburst. So before we drift farther outward into clusters and cosmic webs, it helps to linger for a while inside the life cycle of starlight itself. How galaxies make stars, how they stop, and how whole systems can move from youth to quiet age. Galaxies shine because they contain stars. But stars are not permanent decorations. They are born, they live, they die. And a galaxy's character depends heavily on how many new stars it is still making. To form stars, a galaxy needs gas, mostly hydrogen, cold enough and dense enough to collapse under gravity. Clouds gather, regions compress, a knot forms. That knot grows denser and hotter until nuclear fusion begins. A new star turns on. In galaxies like the Milky Way, this happens steadily but not dramatically. Perhaps 1 or 2 stars form each year on average. That may sound active, but on cosmic scales it is moderate. The Milky Way is not in a frantic phase. It is mature, still creating, but calmly. Some galaxies are much more intense. These are starburst galaxies. In a starburst phase, star formation surges to extraordinary levels. Hundreds or even thousands of stars may be born each year. This usually happens when something has compressed the galaxy's gas. A merger, a close pass, a shockwave. Any event that forces matter inward and makes collapse easier. The result is brilliant. Young stars shine hot and blue. Dust warms. Infrared light pours outward. The galaxy glows with the temporary urgency of creation, but it cannot last. A starburst is, by definition, a burst. Fuel is used quickly. The galaxy burns through its gas and then settles again. There is something beautiful in that temporary intensity, like a cosmic fire briefly visible through the dark. A whole galaxy entering a season of unusual brightness before returning to calmer forms. But galaxies can also stop forming stars. They can go quiet. This can happen for several reasons. A galaxy may simply use up much of its available gas over time. Or its gas may be heated so that it no longer collapses easily. Or powerful winds from star formation and supernovae may blow gas outward. Or radiation and outflows from an active black hole may regulate the gas supply. In dense galaxy clusters, the surrounding environment can strip gas away altogether. When star formation shuts down, the galaxy slowly changes color. Young blue stars are short-lived. When no new ones replace them, older redder stars begin to dominate. The galaxy becomes quieter in appearance, less sharp, less youthful, more like an archive than a nursery. Astronomers sometimes call such galaxies red and dead. That phrase is a little too harsh, perhaps. They are not dead in any absolute sense. They still contain stars. They still have gravity. They still move. They still shine. They are simply no longer producing many new suns. I sometimes think of them instead as elderly galaxies. Their active youth is behind them. Their pace has softened. They drift now in a quieter phase of cosmic life. Galactic winds play an important role in this story. When many stars form together, or when a black hole becomes active, energy can drive gas outward from the central regions. These winds can carry matter far from where it might otherwise have collapsed into future stars. The galaxy keeps shining, but its future is altered. Potential is removed. It is one of those subtle processes that reveals how delicate galactic life can be. A galaxy may contain billions of stars, but its future still depends on whether enough gas remains in the right state. Too little gas, and the galaxy quiets. Too much heat, and the gas won't collapse. Too strong an outflow, and the fuel is gone. So a galaxy's brightness is never the whole story. Behind the glow lies a question. Is this system still making stars? Has it gone quiet? Was it once more active than it is now? Will it be quieter later? The answers shape everything. Its color, its texture, its future, its place in the larger cosmic narrative. And these processes do not happen in isolation. The environment matters. A galaxy drifting alone ages one way. A galaxy falling into a cluster ages another. A galaxy near a quasar, or in the middle of a merger, lives under different conditions than one on the edge of a cosmic void. So the next step in our drift is outward, beyond single galaxies, into families of galaxies, groups, clusters, crowded neighborhoods where the space between galaxies begins to matter almost as much as the galaxies themselves. The Milky Way is not alone. Not in the broad universe, of course, but not even in its immediate surroundings. It belongs to a small gravitational family called the local group. This group contains more than 50 known galaxies, though most of them are dwarfs. The main giants are the Milky Way, Andromeda, and Triangulum. The rest are smaller companions, drifting through the group's shared gravitational field. On human scales, the distances are absurd. On cosmic scales, this is a neighborhood. Groups like this are common. They are among the ordinary social structures of galaxies. But some galaxies live in much denser environments. Clusters, great assemblies of hundreds or even thousands of galaxies bound together by gravity. Inside a cluster, a galaxy's life changes. Not because the laws of physics are different there, but because the environment is busier, hotter, and more gravitationally complex. The space inside a cluster is not truly empty. It contains a thin but very hot plasma, known as the intracluster medium. A galaxy moving through that medium at high speed can feel a kind of resistance. The pressure can strip gas from the galaxy, trailing it behind in long streamers. This process is called ram pressure stripping. The image is extraordinary. A galaxy flying through a cluster, its gas being peeled away like mist in a strong wind. That gas might have formed future stars. Once stripped, the galaxy gradually becomes quieter. Star formation declines. The system reddens and ages. So clusters do not merely gather galaxies, they shape them, they can starve them, they can accelerate their transition into calmer states. Clusters are also rich in dark matter. In fact, the visible mass in galaxies alone is not enough to explain how clusters stay bound. The motion of member galaxies, the hot intracluster gas, and the way background light bends all point to enormous amounts of unseen mass. Dark matter dominates the structure. Visible galaxies become like ornaments inside a deeper gravitational basin. At the centers of many clusters sit giant elliptical galaxies. These are among the largest known galaxies in the universe. Vast, diffuse, old, and often surrounded by huge populations of globular clusters. They likely grew through repeated mergers, swallowing smaller galaxies over long periods until they became the quiet central giants of crowded cosmic cities. Clusters can also be dramatic in another sense. Galaxies interact more often there. Close passes are more common. Tidal distortions appear. Some galaxies are thrown out entirely, becoming runaways, ejected from their old homes. Others are stripped to their cores. Still others merge, though the high velocities in some clusters can also make direct mergers less common than in slower-moving groups. The result is an ecosystem. A galaxy is not just a self-contained object. Its surroundings matter. Its neighbors matter. The temperature and density of the medium around it matter. Its motion through the cluster matters. And beyond clusters are larger gatherings still. Superclusters, flows, filaments, structures so immense that single galaxies begin to feel like grains of dust inside a grand design. But before we go that far, we should linger on one more beautiful tool astronomy uses to understand galaxies inside these environments. A method that depends on gravity itself bending light. A method that turns galaxies and clusters into natural telescopes. Gravitational lens. There are few ideas in astronomy more graceful than gravitational lensing. It sounds technical at first, but the underlying picture is almost poetic. Mass bends space. Light follows that bend, and as a result, a galaxy can reveal itself not only by shining, but by warping the light of something even farther away. Imagine a distant galaxy far behind another one. If the nearer galaxy lies in just the right position along our line of sight, its mass curves the space around it. The light from the farther galaxy travels through that curved space and becomes distorted. To us, the background object may appear stretched into an arc, duplicated, or even wrapped into a ring. These are not illusions in the ordinary sense. They are real images, shaped by gravity. The universe itself acting like an optical instrument. This matters for two reasons. First, lensing tells us about the foreground mass. By measuring how strongly the light is bent, astronomers can estimate how much mass is present, including dark matter. So lensing helps us weigh galaxies and clusters, even when much of their matter is INV.